phenomena that's actually out there, a much more accurate view.
For example, how many sensors do you deploy in this area so that the data you collect will be enough? And you have to first define what is enough, what does it mean to be enough? When you talk about deployment, there are a number of issues to be concerned with. One is the sensing range. Each device has a limited capability of how much area that it can sense. And also you have to think about the communication range of these nodes. And you have to think about how much battery do you need to install in there. And of course there's a fourth one is the cost.
Another example of using wireless sensing to monitor environmental conditions is being conducted by Harvard's School of Engineering and Applied Sciences.
There's been a project run by a group at Harvard that's measured volcanic activity on a couple sites in South America. Particular benefits there were early warning systems.
What they did was to go to the volcano, the Vermont there, and they deploy these sensors over there to collect data, the vibration data basically, the seismic vibration of the ground.
They then used a radio modem to transmit 10 miles back to town.
A wireless sensing network retrieves and transmits data. As these networks become more complex, the science to manage them also increases in complexity. One begins to wonder, what is the most important science behind these complex systems?
Computer science, I would say, because sensor nodes are computers, miniature computers. They have processors, memory. They can communicate. They have a transmitter, receiver. So hardware and software is there, and they have to be programmed to function, right?
The name computer may not be the right term, but we're stuck with it, just like everything else. We're not just computing as number crunching anymore. We are really into the business of communication a lot, web, internet, and so on and so forth. Everything is data. Your documents is data. Your medical records are data. Even your science project, your graphs and so on. These things are all data. And my specialties are mostly on the storage side and accessing side. So how you store data in an efficient way, how you access data in an efficient way. Remote sensing is somehow, you can say, it's a data collection device. Once it's deployed, also you are concerned with which sensors, which nodes should collect data for you, how often they should collect data for you, and so on and so forth. These are all relevant questions to ask. So from the question perspective, you want to say, well, in our database systems jargon, we talk about the user queries.
So maybe what I want to do is just drop these things out there and allow them to figure out, okay, I'm next to this guy, so I'm going to send data to him, and this guy's going to send it to her over there, and vice versa. So you hop the information from one place to the other. So you're creating this network which is kind of automatically configuring.
The best is to store that in themselves. I'm a sensor node. I just made a reading of the temperature around me. I want to store that in myself. But I don't have indefinite amount of memory. What am I going to do? I want to send it to my neighboring node. But which node? The sensor node has to find a way of delivering this data across the network, which will consume battery power. Okay? So if the sensor node is selfish, it wants to keep all the data within itself, and when we have a question, send it to me, and I will deliver my answer. So the concept is to store the data within the network, anywhere within the network, considering the cost, which means battery power consumed to store the data and battery power consumed to deliver the question and then process it and then providing the answer. So what's gaining attention is multi-tier network. The base station is powerful machine, and then there can be different tiers. Okay? So the tier that's close to the base station has generally more power, but we need fewer of them. And they're not the ones that are at the front end collecting data. I mean, if you think of that in the hierarchy, at the bottom, a large number of them. and then they are talking to their immediate supervisors. Okay? It's called tree-structured routing protocol, and they just keep sending data to what's called sync, which is a more powerful machine that has its own power source and more computing power. So they have to keep sending their readings to this base station old sync.
So they spend most of their time in a kind of a lower power mode, kind of checking to see if anything's going on. But then if any one of these devices detects something abnormal, they all just get active and they start sampling.
Although the transmitters on board these can only transmit about 100 meters, to hook them up to a single sync node that's connected to a radio modem, and now you have a 40-mile range of transmitting data line of sight. If line of sight isn't a possibility, then you can also use a cell modem.
So each sensor node has to make a decision on its own, just based on what it has and what neighboring node has locally, in such a way that when we see in the entire sensor node of hundreds of thousands of nodes, overall the energy consumption will be minimum. It's a very challenging issue.
Another application of wireless sensing networks is to track the movement of people and equipment, with obvious military applications.
All of this was really motivated by the military.
For example, vehicle tracking. I can distribute a number of these along the roadside with proximity detectors of some sort on them. Then if a vehicle moves through this field of sensors that I've deployed, as the vehicle moves, the sensors in closest proximity to the vehicle will report data that, hey, I see something in my field of view here.
You can talk about the peripheral defense. You put around you so that you can say, well, are there intruders or not? And of course, this border defense.
Another use of wireless sensing, closer to home, is in our houses and office buildings, what is being called smart buildings.
So far we've been talking about monitoring the environment where the end user is a person, okay, a scientist that wants to understand what's going on out there. So the next wave is to get the human out of the loop, okay?
The smart building has a number of aspects to it. One is the building itself is smart. If you kind of tilt it a little bit here, the stress at this certain place is too much, and then the sensors form a certain central server saying, hey, there's something going on there, you better work on it. Or even better, if the building is really smart, they can actually adjust itself back. So that's the kind of a structural smartness.
So machines, now that they can sense particular things, should be able to communicate to other machines. And one really interesting application for that is a home where your refrigerator will communicate with the washer and dryer, which will communicate to the deep freeze. And the idea there is that you really don't want all these things to be on at the same time, because that increases the peak energy needs of the house. So you'd like to distribute the running of each one of these devices separately. Okay, that helps. If everyone was doing that, that would help the power plants basically back off the power that they would need to generate, because they're generating to a peak demand. So if we can kind of spread out the demand within one house and among multiple houses and within neighborhoods and towns, then the amount of power that needed to be generated at any point in time could be reduced.
The other smartness of the smart building is the interaction between human users in the building and the building itself. Like you carry a laptop somewhere, you don't need to kind of log in here and so on and so forth, and it just connects you to the right place, for example. Whenever you want to talk to somebody, a phone call will transfer to your desk, but you're sitting here. Oh, you got your phone call from here. So this is another kind of smartness.
So they can make your life easier. Okay? Once you come downstairs, they know you are there, and then the temperature setting will be raised, you will have more comfortable temperature and the coffee pot will be starting to brew the coffee. And it may be a spooky concept, but
and figure out where the lights are on and should we turn them off. So if you had a network like that inside of a building, you could have more smart control over what's going on inside. Okay, you could automatically shut down the lighting in rooms where people aren't. Okay, I think that's probably the next big thing.
More and more so, I believe sensors will appear lots of places. And the geolocation, geoinformation of these sensors will be useful for people to understand the environment, the Earth. What kind of data do we have in these particular locations? The other side of the applications is in cities. People start to put the sensors on your traffic lights, for example, and in there cameras are used a lot. And in the city, more like privacy becomes an issue. If somebody get the data and connect to your personal behavior, that becomes an issue that people may not like to see.
Well, I think the one exciting thing about this area is that it really helps us to understand more about where we're living and what we're doing and how we're impacting our planet. One thing that sensor networks allow us to do is get information on what's going on out there. So it's a nice way to leverage what people are doing in the commercial space to kind of answer some other problems or other questions that we might have.
It's a cool factor as well. You know, if you look at the sensors deployed, you know, these small devices, you know, the data that's kind of pumping back, and you see the, you know, the lights are kind of blinking, and suddenly, you know, brings me back to my childhood. Actually, at that time I was playing these devices, right? After a while, they disappeared. I only have a computer now. It's a monitor and a keyboard, right? And what's exciting is that, you know, it goes back to these things again, but of course it's at a different level. And you see these things kind of collecting data and see these things work. I think it's exciting. It's kind of cool. Very, very exciting field to work in.
Remote wireless sensing is certainly an exciting science. We're able to increasingly sense and track our environment in ways that were previously difficult or impossible. As a society, we'll need to examine the trade-offs between improving daily conveniences with our desire for privacy. We'll need to decide between using this information for collective good and protecting our own personal freedoms. I'm Amy Seidel. Join me next time for more Emerging Science.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.